Okay, so as I was saying last time, today is going to be the last day in terms of topics for the exam that we have next Wednesday. And I'll be done with it for sure today. And then Monday of next week, it will be mostly for like office hours type thing. So like if you have anything that you want to go over with me, like you can come to class, but I don't plan on lecturing at all on Monday. Because it doesn't make sense to start since we have the spring break, like for whatever things you say during those 20-30 minutes, like it would get lost. So it's better to just start fresh um, after the spring break with new material, which will be duality, which is actually one of the more interesting topics of this class. It has like many like useful applications. It's actually related even to Lagrange multiplier, so we won't do that because multivariable is not like a requisite for this class. But okay, let me explain what the situation was from last time. So last time, what I was saying, okay, so this is what we were doing last time. I had, uh, as usual, an optimization problem. Okay. I had an optimization problem. In this case, one of the inequalities happens to be naturally written first as a greater or equal to 1. Okay, so if you kind of first draw the region, it looked like kind of like this quadrilateral. But then the idea is that, and this is where you have to be cautious, right? When you write it in the usual notation, you have to turn it to a less or equals 1, less or equal to. So that can be done easily just by multiplying by -1. Um, but that does have like an interesting effect because um, when you add slack variables, right? If you add like a slack variable for each of these like inequalities, you still have like the identity matrix as usual, but now you had a negative coefficient here because we had to multiply by -1 here. And that may not seem like a big deal, but the problem, and this is kind of like implicit when I mentioned the simplex method, but it wasn't really that important until now. Uh, No, yeah, at least it can be dropped a little bit more. So the problem is that in the simplex method, if you think about it as an algorithm, step one, I think I called it, or step zero, is that you have to start with the basic feasible solution. So if implicitly, we had never worry about that because before you would always get like this identity from the slack variables. And then you would use these coefficients where it happened to be positive in all the examples we were doing. So the feasibility, which is like the non-negativity of each variable, is kind of like guaranteed in this case for free. So there's nothing to worry about. But now, if you take as a basis like these two columns, right? If you take as a basis these two columns, then the basic solution would be like 4, -1, and the rest of the entries are 0, and then that one would be negative. Okay. And again, you could try to find another basis, but kind of like the way you have to approach this problem is to imagine you have like a titanically giant matrix, which is like 50,000 times 100,000. There, you're not going to start scanning columns to see which one is like a basis that which is feasible. Like when you got before, when it was always the identity with positive constants, then you're good to go. But like you shouldn't try to just like do trial and error, because the moment you start doing trial and error to find a basis, then basically you're just examining all the corners, and then you're like, you might as well not use the simplex method for that if you're just going to go through all the possible bases to see which one is feasible or not. So the idea is that we have to find a way to produce a basic feasible solution, and then we can start the algorithm. But to produce that solution without actually going just by trial and error. Okay, so let me copy the system of equations from last time into my other slides. Okay, so this was like the system from last time. And so again, like the idea is that we want to find, this is today's goal, and that's like the only thing I'll do for today. We want to find as basis, a basic feasible solution that is used to start the simplex method, without trial and error. Okay, so the first thing, as a convention, it is convenient, it's nicer, which I'll use whenever you have the system when you have the system in equation form. We will make every entry of B non-negative. We will write it so that B is greater or equal to 0. And so by that, I mean that every entry of B is non-negative. Okay, so if you look at this system, clearly it's not in that format because, like there's a -1 here. So, but, that is not like an easy thing to fix. It's kind of like the same with the inequalities. You just multiply by -1 everything, and that would, so whenever, even if one of the coefficients of the vector B, or one of the entries of the vector B is negative, you multiply everything by -1 in that equation, and then it turns it into positive. So let me do it here. Oh, sorry. And I should have added, in this case, that x3 and x4 should be greater or equal to 0 as well. I forgot about that part. So we're finding the max of x1 plus x2, where x1, x2, x3, x4 are all greater or equal to 0. And then x1 plus 2x2 plus x3 equals 4. And then I'll multiply the second equation by -1 in order to have positive constant coefficient. So I'll write it as x1 plus x2 minus x4 equals 1. Is that okay? So far, so good? Uh, okay, and now comes the new part, which is like the thing that we have to discuss for today, which is to find the basis, we will solve an auxiliary system. So I'll kind of explain what that means. So to find the basis, we solve a different optimization problem. Which I'll call like the auxiliary problem. Okay. So I'll kind of explain what this is. So again, this is a new optimization problem. Since this is a new optimization problem, there's a new optimization function. So I'll write it as a max problem. And I'll kind of keep a secret for now what the max of that we're trying to find, because that's kind of like the fun part of this problem. So it's a new problem, okay? The idea is that we will add two new slack variables, and you'll see why in a moment. So I'll kind of like, I'll put the new stuff like in a different color. So I'll have two new slack variables. So let me write them in like why two? Because there were two equations. So you added a slack variable per equation. So one slack variable for each equation. So in this case, like there were two equations, right? And then that's why we were adding to the new slack variables, and kind of like they get used in exactly the same way as before, uh, which is like, like usually the slack variables like it just gets added at the end of each equation. So I'll do the same here. Sorry, like the new ones are 5 and 6. So plus x5 equals 4, x2 plus x1 plus x2 minus x4 plus x6 equals 1. Okay, so again, um, so I'm adding the slack variables, and here's like the thing that can be confusing, and actually, this is related to the function that we're optimizing, right? Uh, because again, what am I trying to do? What I'm trying to do is to find a solution to the original equation, right? Uh, we're trying to find a solution to this equation, which happens to be feasible. So where like all these inequalities are satisfied, right? If you had a solution to this, right? If you had a solution to the original system of equations, right? Um, what would be the value for x5 and x6 if you had a solution to the original system of equations? What would you say? It would be zero, right? Like each one individually is zero. So this is set up, like let me make that as a remark. The new system of equations is designed so that a solution to the original system of the equations happens when like the new variables are zero. So this new system is designed so that the new slack variables are zero precisely when we have a solution to the original system of equations. Actually, I'll write it first as a mean. I'll write it first as a mean because a mean is kind of more natural than a max, and then I'll kind of like turn it into the max notation. So, but it does make a little bit more sense to understand the first as a minimum. Okay, so what are we trying to do? What we would like again, and this is a new optimization problem. So the idea is that I'm free to choose a new optimization function. So if what I'm trying to do is solve the original system, what I'm trying to put is like a function whose minimum agrees happens at the values where x5 and x6 are zero, right? Because if like I'm trying to if I minimize a function that has a mean and x5 and x6 are zero, then that would produce by the simplex method like the optimal solution to this problem would give me a feasible solution. So the question is like, what is a function that whose minimum happens where those two numbers are zero? So for example, here's one, right? That is like a look at this function. Like how what would be the best, like this function like x5 plus x6, right? That's not negative because we're looking for slack, like we're making the assumption that the variable should be non-negative. So if the minimum is achieved and happens to be zero, that would force x5 and x6 to be zero. Okay, so what I'm trying to say is that if mean, let me put it like the choice of the optimization function is the following. So we're choosing x x5 plus x6 as the optimization function because the mean of this function being equal to zero happens exactly, occurs precisely when what? How is that, how can two non-negative numbers add up to zero? They add up if each of them is individually zero, right? So the solutions to the original problem, to the basic feasible solutions of the original problem are the same as those solutions that minimize this function with value zero, okay? Where like the minimum is zero. So the basic, let's call this, sorry, I'll call this OR for original, and this one I'll call it aux for auxiliary, because otherwise like um so the point is that the basic feasible solutions to the system OR correspond to minima of the system auxiliary system with minimum value equal to zero. Okay. Is that making sense? Kind of like the idea behind it. So, yes, yes. I think now I can, if I zoom out, maybe. Right, because the idea is like, again, it does take some time to get used to it. Like, you know, here's how you should think about it. If for some miraculous reason you already have a solution to this system of equations, right? If you already had a solution to the original system of equations, then automatically these two have to be zero, right? Because all, like, these two already match without the need for x6. So, but of course, we don't have a solution, because otherwise, why am I doing this? So you have to pretend that you start with something that is not a solution to the equations. Um, and so because of that, there might be this extra term, right? Like this junk stuff, which is like what the slack variables account for. But then if we somehow try to minimize these two quantities, right? If we try to minimize these two quantities using the simplex method, and that minimum happens to be at zero, then that minimum solution would have been like a solution to the original system. It is like, if you think about it, like a very clever like setup. So it's kind of like trading off. Just to start the simplex method, you kind of like do the simplex method for something entirely different, so that you can find the basic feasible solution. But the idea here is that you don't go by trial and error, because you just let the simplex method guide you through the, like, find the basic feasible solution for you. And this is actually how like most like algorithms work in practice. Because in practice, again, in practice, you have tens of thousands of variables or hundreds of thousands of variables, you know, some which will be less or equal inequalities, others greater or equal inequalities, other just like equations, like it's like a mess. So when you set it up like in the equation notation, like it may not be obvious like that you have like a basic feasible solution. So first what you would run is like this auxiliary system to find a basic feasible solution, and then you run the problem that you wanted to solve starting with that one. Okay, so this is like actually, so usually like in practice, like the simplex method is done as a two-step process, like, so in practice, in the real world, like, in the real world, you would first solve the auxiliary, first solve the auxiliary system, find a basic feasible solution, and use that solution and use the basic feasible solution that you find. Well, let me go scroll up a little bit. To start the simplex method for OR. Simplex method for the original system. So I don't know if you have been reading the book, which is actually pretty interesting. Like I do like that book a lot, because it does have a lot of like interesting conversations about like efficiency and other things. So I think this is probably like the preface or like the chapter one of the book, but they do mention the authors are like, there is a sense in which finding the minimum solution or the maximum solution is takes as much time as finding just like any basic feasible solution. Because if you look at it from this perspective, to find a basic feasible solution, you have to run a simplex method. So to find the optimum solution, you find that you use the simplex method, but also to find a basic feasible solution, you use the simplex method. So they both are using the simplex method. So in a sense, those two problems are not that different. So if you have like basically what they are explaining, if you read the book at the beginning, is that if you have like an efficient algorithm for finding a basic feasible solution, that is more or less in terms of like computational time, as if like the optimum won't take that much longer because they're kind of like built on the same approach, which is kind of like cute. So I mean, I do think like this course, there is like it's kind of like linear algebra. Like, if you look at linear algebra, like the algorithms themselves are all like matrices which you row reduce, but like there are a lot of like useful concepts, like, it's kind of like they're very deep concepts, but like the implementation is very simple because it's just like arithmetic, over and over and over and over. The same kind of happens here, where like there are actually very interesting ideas in linear optimization, but once you kind of get to the right idea, like the implementation is just, very algebraically tedious, but you know, it's not like calculus, where like you have to be very clever when you solve an integrate or like differentiate. Here it's just like always the same. It's just like finding the right algorithm where like, you have it kind of have to hit the jackpot. Like once you have the right algorithm, everything collapses to like matrix operations, and that's kind of like how linear algebra works in general. So now, the way I wrote auxiliary system was in terms of mean, but as you may remember, all our problems are as maxes. It's just that this was like a little bit more like natural condition to explain. But remember, if you try to find a mixed problem can a minimum sorry, not a mix, a minimum problem can be turned into a maximum problem just by multiplying everything by -1. So in fact, this is the same system, and this is how we will work it. Like the version I'll use for this system is with, like, I'll just multiply every entry by -1. And okay, it's kind of implicit in everything that I do that all the variables are always non-negative. So I just don't want to keep writing that because otherwise it takes me forever. Um, and this is like ready to go. You'll see what happens here once you write it in matrix notation. So if you write it in matrix notation, let's see. So like I'll write the names of the columns just to help you out. I'll keep the two last ones in green because those are the new ones. Oh, sorry, let me put this. Okay, so this is the, this is the auxiliary system. The ordinary system, the original system, the equations would not have included these columns, right? So basically what you're doing is add up a column, an extra column for each equation that you had, okay? Is that making sense? But now almost I mean, by design, the new columns give you your mini 2 by 2 matrix here in this case. So this one has like this is like a mini 2 matrix, and maybe it's useful to remind you how this was supposed to work. So since the basis had to consist of 2 columns, right? So the basis was 2 columns. In this case, because like the matrix is 2 by 6. So here I'm using columns 5 and column 6, right? And so like if you wanted to find the values for the basic variables, like you had to solve the system of equations, but there's nothing to solve, right? Because it's the identity matrix. That's the point of using the extra variables. And then all the other variables are set equal to 0, right? So the basic solution to this system that we start with, the simplex method, is this. So this is like the solution that starts this, where we start the simplex method. So this is the basic solution that starts the simplex method for like the auxiliary system. Oops. Where simplex method for auxiliary begins. Is that okay? Yeah. Oh, like that I copied something like let's see. Oh, okay, let's see. One, two. Oh, I that I dropped a 2, you're saying, or let's see. Oh yeah, thank you so much. Okay, you saved me. Yeah, so you're saying because there was a 2 here, right? Whew, thank you. Yes, yes. Yes. Be very careful when you're doing these things, because like it's kind of like a very frustrating experience when, like, you dropped a 2 and everything gets kind of, I mean, this kind of like changing a one coefficient could ruin the entire system, in the sense that there's no basic feasible solutions. I mean, that there's no minimum for the new one or whatever. I mean, it can be very, like, yeah. Actually, let me check on my notes to make sure like nothing else was done incorrectly. But yeah, you do have to be very careful. Yes, I do have it. The rest seems fine. You do have to be very careful with these systems, because it is easy to kind of like make a arithmetic mistake. They're bound to happen because there's so many things going around. Um, but now we're good. Yeah, so just put a 2 here in those columns. Is that okay? And then to start the simplex method, you just have to add a new row, right, for the optimization function. So you call z the optimization function here. Z was like negative x5 minus x6, or x5 plus x6 plus z equals 0. So the entries of those numbers, the coefficients of those variables make up the this is what makes up the last row, the extra row that you add. So again, my recommendation, to just remind yourself that that has nothing to do with the original matrix, is you should put like this horizontal row. Um, And the coefficients are 0, 0, 0, 0, 1, 1, 1. Is that okay? So now this is ready to go. And again, the column for Z is not that necessary because Z will, that column will never change as you work through the method, but like the last row is definitely important. But I do like to keep the Z column just because like it reminds you how you're reading everything out. Um, so far so good. Okay, and then something that may look fishy is happening here because you might say, okay, but if I stare at that matrix, none of the entries at the bottom are negative, right? So wouldn't the simplex method terminate already? And that is where you have to be careful because according to the simplex method, that can be done after, remember, like the point of the simplex method is that our basis is x5, x6, right? So the rules is that if the basis is this, any number except this one and this one has to be 0. So we are still for these columns, right? So if the columns are x5 and x6, one can only appear one time. And here one is appearing two times, right? One is here, and one is here and here. So this is still not in the correct presentation because you can only read the thing about the coefficients when like there's zeros everywhere else. So this is also important to kind of like notice. So let me make it as a remark. It is not an issue. This does not mean that not mean that the simplex method is over. Because like the presentation does require is that for a basic variable, the one can only there can only be one on that column for the basic variable. Like that sounds very weird to say, but because one can only appear once on a column of a basic variable. Okay. So that means that you have to use this one to make zeros, and then you have to use this one to make zeros everywhere else in the column. And once you do that, you'll see that negative numbers do appear below. So that's, I mean, again, that doesn't really was something that we had to worry about at the beginning. But because at the beginning, like for the optimization problems that we have been working with, the function that we were optimizing was written in terms of the original variables. But now this function that we're working with is being written in terms of the slack variables. So that's the difference. Usually, like the optimization function was always in terms of like the original variables, not the slack ones. So that's kind of what creates like the discrepancy. Uh, but so how do you make zeros? Like you can make minus row one. You know, I'll do both operations at once, but you do have to be careful with that. So I will do minus row one plus row three into row three. And then I'll also do minus row two plus row three into row three. Usually it's not good to do two operations on the same row at once, but like, in this case, it doesn't cause that much of an issue. So I'll copy paste this, but I'll give you time to copy it because, like, if you're doing it, if you're doing it on paper, like, it definitely takes more time. So let me erase this here first. I'll erase the third column because like that's what's going to change. Okay. So let's see what happens. So you're subtracting row 1 and 2 from row 3. So you get 0 minus 2, which is negative 2. Oh, sorry, yes.
So is the point of subtracting row 1 and row 2 from 3, just to get rid of those two ones?
Correct. Yes, yes, yes.
And then we'll have a bunch of negative.
Correct, because the rule is that the thing is like, and I had mentioned this such a long time ago, but the rule is that the optimization function must be given explicit in terms of the non-basic variables. So here, because we chose x5 and x6 as basic, you're writing the optimization function in terms of the basic ones, not the non-basic ones. So that is, which again, it was never like an issue before because before, like naturally, like the function was like it's always written first in terms of the non-basic one. So like it's only in this method with the auxiliary system that kind of like the roles are a bit reversed because like the function itself is related to the slack variable. So that's like the main difference. But yeah, on a more practical level, you can just think about it. Oh, we wanted to make negative coefficients, right? And so and the rule was to have like just one on each column. So that's also what's happening here. So okay, so you subtract 0 from 2, then you subtract 0 from 3, right? So that gives you -3. Then you subtract 0 from 1, that gives you or 1 from 0. So like I'm saying it backwards, but you know what I mean. Then the other ones gives you 1. Then now this one gives you 0. Then this one gives you 0. And this one gives you 1. And then the other one gives you -5. And now this is starting to look more like familiar territory, right? Like now this kind of more or less looks like the regular stuff, like the regular type of problems. In fact, once you kind of like go like this auxiliary system has like two important steps when you added the extra variables and when you do these kind of like row operations to kill the ones, right? Once you do that, this is kind of like indistinguishable from everything else we have been doing so far in the course, like with the simplex method. So this is kind of like the two main the two main steps, because now you'll see let me I'll kind of like start solving these systems. I well, I still would do the copy paste. Of course, you can kind of like save yourself some steps because I wouldn't expect you to copy paste like the system so many times. But the idea is that you look at the largest negative coefficient, right? Which is column -3. You do the ratio stuff. The ratios are what? They are 4 divided by 2, which is 2. And the other ratio is 1 divided by 1, which is 1, right? So the smallest positive ratio is the second entry, right? So let me box that one. So that is a winner in the simplex method, right? Uh, so again, what that means is that this is the one, again, just to remind you what this means. What that meant is that you're going to turn one of these basic columns into non-basics, and the swapping is going to occur with x2. So the one who won is like this entry. So the idea is to make zeros above and below this entry. So how do you make the zeros? You do the row operations, which are -2 row 2 plus row 1, and then 3 row 2 plus row 3. And that would take care of it. So let me, in the exam, I'll give you systems that are really quick to solve, because otherwise it would take you for eternity. So no, don't worry about that. Like they won't be that long. And it's also only for problems because, in part because of this, like, because this is a tedious, but like everyone tests different skills. I mean, they're always simplex method, but they're kind of like slightly different setups of the simplex method, and, perturbation or this auxiliary system, figuring out whether it's unbounded or not. So, okay, so when you do -2 row 2 plus row 1, you get -1, you get 0, you get 1, you get 2, then you get 1, -2, and then you get 4 minus 2 is 2, right? Woo. And then you do 3 row 2 plus row 3, you get 1, 0, -1, -2, 0, 3. And then this one gives you -2. And I'm going to check everything here when I wrote my notes just to make sure like it was all fine. Yes, we're good. Questions so far so good? Okay, now again, what is the next step? Largest negative coefficient here would be this column, right? What are the ratios? Ratios are 2/2, which is 1, 1/-1, which is -1. You need to choose the smallest positive ratio. So you choose the first entry, right? So you choose that first entry here. Okay. This entry must be turned into a 1, and after you have turned it into a 1, you make zeros everywhere else. So it's to do that is easy. You just do row 1/2. So let me divide everything here by 1/2. Oh, sorry, divide everything here by 2. So I get -1/2, 0, 1/2, 1, 1/2, -1, 1. Is that okay? Is that making sense? Ooh, okay, and again, this is our main interest. Now I turn this one into a 1. I will make zeros everywhere else. So how do I make zeros everywhere else? I'll do row 1 plus row 2 into row 2, and I'll do 2 row 1 plus row 3 into row 3. So the first is just adding the rows, so you get 1/2, then you get 1, then you get 1/2, then you get 0, then you get 1/2, then you get 0, right? And then you add the other ones, you get 1/2, row 1 with row, oh, sorry, 2 row 1 with row 3. So because it's a 2, you get 0, 0, 0, 0, 1, 1, and 0. Is that okay? Is that making sense? Questions about it? Oops, and I forgot to, what is this? R1 plus R2 into R2. Okay, so this should be 2, right? I forgot to write that one. Let me check. Yes. So far, so good. Okay, so note, it's kind of like fun to, now here we do stop, right? Because now everything is positive, like at the bottom. What is the difference now? Now the difference is that the essentially what happened if you kind of kept track of everything. What happened is that when we started, sorry, just to go back for a second, when we started the simplex method, the basic variables were x5 and x6. Okay, because I was choosing this identity matrix. That was the basis that I was choosing. Um, sorry, oops, here you are. So, and the simplex method, like it was x5 and x6, right? Because this was like the the identity matrix I was choosing. And even though this was 110, right? Now it's still 110. The difference is that now this is fine because these are now non-basic variables. And I turned these both into non-basic variables. In fact, the basic variables are now, what is my identity matrix now? The basic variables will always be the ones that are just like one and zeros, a one somewhere and zeros everywhere else. So essentially now uh, the 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 basic variables are x2 and x4. And so everything that's not x2 or x4 is turned automatically equal to 0. So the basic solution is x1, x2, x3, x4, x5, x6, right? Because this one had like, this is like the auxiliary solution, right? So everything that's not x2, x4 is 0 automatically, which is important. That tells you that x5 and x6 is 0, which is what we wanted, right? Like we wanted like the last two slack variables to be 0. Um, and then what is x2 and x4 from here? They're just like the coefficients that you see here. So x4 has to do with 1 and x2 would go with 2. So this would be, so you just have to check like the coefficient. So like the coefficient 1 is in x2, but x1, x2 is associated to 2. So it's kind of like read this like in this way. And x4 has to do with 1. Is that making sense? Questions? So this is the auxiliary solution. The basics, like the to solve the original system, right? What I'm going to just do is forget about the last two entries because the last two entries were like added artificially. That's why these sometimes are called like artificial variables, because these last two entries were added artificially to solve this problem. But the original system, right, like the very basic system of equations we had no x5 or x4. So when we go back to the original system, for the original system, there's no x5, x4, no x5, no x6. So it's just like the first two, four entries of this vector. Okay. And the basic variables are columns 2 and 4 because those are the ones that are non-zero. Okay. So let me put here back to the original system. So this is where officially the auxiliary system ends. Okay. Now you can use what you just found to start the simplex method on the original system, which is what I'm about to do now. Like on the exam, I would just ask you to find the auxiliary solution. Otherwise, it's to parse and each one would be too long. So yes.
Yeah, I specify the auxiliary solution, but do you want us to take out the extra variables?
No, I do leave the extra. I mean, they will be zero. Like, but yeah, you should leave them as like the longer vector. Yeah. So do keep them as a longer vector. In fact, as a comment, is that just before I forget about this, if this number had not been zero, we needed this to be zero because we wanted to force them both to be zero, right? So if you had terminated the simplex method at a number that's not zero, that means that there was no basic feasible solution of the original problem. So the original problem cannot be solved at all. So it must terminate at zero. On otherwise, there's no solution to the basic. There's no basic feasible solution. That's actually a important concept. So if this is not zero, original system has no basic, so has no feasible solutions. So like in practice, like you should expect to get zero, but I'm just saying like as a theoretical thing, um, if it's not zero, there wouldn't be solutions. Yes.
So like the X original you have, is that like the maximum or is that like the basic solution to start simplex?
Oh, right. That's good. This is not the max. This is just where you started. Actually, I can show you, like, let me copy paste the picture from last time. I was going to mention this. Let me copy paste it in the new notes. See, this was like the original region, right? This was the original region of the problem, right? This is kind of like the shadow, right? Like that's what we have discussed before. Because like really like the convex region, right? The convex region is in four dimensions because it's x1, x2, x3, x4. Like the shadow of the convex region onto the plane is this quadrilateral. The first two entries, right, give you the shadow of this point. So like it would, sorry, like 0, 2, or did I, oh my God, I drew it. Okay, this is 0, 2, right? Like this. Oh, this is so silly. Right. So the shadow, like the simplest method is going to initialize here. So this is where like this matches to like corresponds to this corner. And if you look at the max, what is the max of x1 plus x2? I mean, you can just kind of do it by like adding that quickly. This adds, like you're just adding the two coordinates, right? This adds to 2, this adds to 1, this adds to 1, this adds to 4. So like the max is actually here. So the simplex method should take us, what it's going to do is that it's going to, now to the on the original system, the simplex method is going to take us from this corner to this corner. And it should only be one step because I mean, there's only one, because it always finds the most maximum, like most efficient way. If I mean, you could go this way, this way, this way. That would be three steps, but that happens if you just don't choose like the largest coefficient. You see, like because that's why we're always choosing like the largest negative coefficient in the simplex method because that's the one that gives you the maximum increase. So if I mean, there are other rules to do the simplex method which could take more steps. But like if you go through this way, I think this time we should just it should be relatively fast to solve it because it should jump us, take us from this edge to from this corner to that other corner. So yeah, for those who are watching the recordings, like it should go from the simplex method. If we do it correctly, it will take us from here to here. Um, but yeah, so it's a good example because it shows you that you don't. I mean, sometimes maybe you would get lucky and it happens that it gives you like the max already. In which case, it should be really relatively straightforward to notice that once you kind of try to solve the original system. But it doesn't require to take you the max. It will take you to one of the corners for sure, and that's good enough to start the method. Okay. Does that make sense? Kind of. Okay, so let me solve the simplex method. Now that we have like a starting point. So again, let me write. Now you call z again in the simplex method called z the the function you're maximizing. So this is one. So z minus x1 minus x2 plus z equals 0. Okay, so what is the matrix format? It would be x1, x2, x3, x4. I'll put the column for z already. I'll put like the augmented thing. Okay, so it's going to be 1, 2, 1, 0, 0, 4. And here I have 1, 1, 0, -1, 0, 1. And then let me put the horizontal line for the entries of the optimization function. And so that gives you what? -1, 1, 0, 0, 1. Okay. And this is augmented with 0. Let me make these brackets a little bit smaller, just so that it looks a bit better.
That's still also negative.
Oh, let's see. Oh yeah, thank you, thank you. Good catch. Whew, perfect. And so my basic, what I'm saying is I'm going to start the simplex method with x2 and x4 being the basis, right? I want them to be the basis. Oops. And so, but again, what does it mean to be a basis in the simplex method? That has to be made explicit. What it means to make that explicit is that you have to have like the identity matrix, meaning that you have to turn these columns into zeros and just 1, 1, and zeros and just 1, 1. Okay, so like the basic, like the point of the simplex method is to make the choice of basis explicit. This is not like an explicit choice of basis because you don't have the identity matrix in these two columns. So you have to do row operations to turn them into the identity matrix. So how could you do that? For example, I could try to make a 1 here, right? So I'll divide row 1 by 2, and now I'll turn this into a 1, right? Because it's negative right now. So I'll do row 1 over 2. And negative row 2. So what does that give me? So again, I'm dividing the first row by 1 by 2. So I'll get 1 half, 1, 1 half, 0, 0, and 2. And then I'm multiplying every element in the second row by -1. So negative, negative, plus, so this becomes +1. And then -1. Is that okay? That's fine. Now this is looking closer to the identity, but let's just focus on one column at a time. So again, the idea is that the rule is that you want to make only an appearance of a single one in each column. This is already good, taken care of, right? Now I just have to use this one to make zeros everywhere else. And after I have done that, then the presentation will be ready. So I'll do what? I have to do row 1 plus row 2 into row 2, and I have to do row 1 plus row 3 into row 3. Oh, sorry. Let me copy paste the other one. Oops, take it back. Let's see, copy paste this one. So when you do, let me erase this too. Okay, so I add the row 1 with row 2, I'll get -1 half, I'll get 0, I'll get 1 half, I'll get 1, I'll get 0, I'll get 1, and then I add row 1 with row 3, I'll get -1 half, I'll get 0, I'll get 1 half, I'll get 0, I'll get 1, and I'll get 2. Is that okay? Is that making sense? And so you see now columns 2 and columns 4, right? If you just focus on columns 2 and 4, you do have like a version of the identity matrix here. So that has made them now it is explicit that those are the basic variables. Okay. And then, which again, like you don't cannot notice that until now, because until now, when you added the Slack variables, you always got the mini identity matrix for free. So that was perfect. But here you do have to do more work. But now once you have it here, like you can just like apply the simplex method as before. Like we have to look at the largest negative coefficient, right? There's only one option here, like the negative 1/2 on the first column. And the ratios are 2 over 1/2, which gives you 4, and then what? 1 over negative 1/2, which gives you -2. But of course, again, you want to use a positive one. So like our winner is going to be 1/2. And so I want to make that into a basic variable. So that means that I want to kind of turn this first into a 1 and then use that 1 to make everywhere zero, or everywhere else zeros. So you do 2 row 1. So that gives you 1, 2, 1, 0, 0, 4. Okay. And then finally, you make zeros and everywhere underneath that 1. So I'll do row 1 over 2 plus row 2 into row 2. And then I'll do row 1 over 2 plus row 3 into row 3. And let's see, what do I get here? And hopefully, I think this will be the last step, if I'm not mistaken. Right. So this becomes a 0. 2 over 2 is 1. 1/2 plus 1/2 is 1. Then 1. 4 over 2 is 2. So it becomes a 3. Then it's a 0, a 1, a 1, 0, and then 4. So yeah, we're supposed to end here. Is that okay? So a stop. What are the basic variables? Are those where we have like the columns of the identity matrix. So we have a basic variable here, we have a basic variable here. Okay, so x1 and x4 are basic and the rest are non-basic. So x1, x4 are basic variables. Else is non-basic. So the vector would be x1, x2, x3, x4. 2 and 3 are automatically 0. And what are the values for x1 and x4? The value for x1 goes with the coefficient here. So that would be 4. The value for x4, sorry, the value for x4 goes with the coefficient here. So it would be 3. Okay. And this is the maximum, the optimum value. So this one does maximize, right? And if you look at the shadow, right, what is the shadow of this vector? The shadow is 4, 0, right? It's the first 2 entries of the vector. And if you look at the first 2 entries of the vector, what is the 0.40? Sorry, just to go for a second to the picture. What is the 0.40 is the max that we had discussed before. Okay, and you can see here that for this number corresponds to the value for the max. So everything can be read off from the last step, like which is kind of like the cool thing. Is that okay? Is that making sense? I mean, so of course I went like carefully, but every auxiliary problem is the same. You add a slack variable for each equation. You get like, so that you solve like you change the optimization function to like just like the negative, the sum of the like it's the mean of the sum of the new slack variables basically. You solve the auxiliary system, and that allows you to start the new one. So let's stop here, and then which is the last topic for the exam. And so on Monday I won't lecture at all. So if you want to ask me anything specific about any problems, we can discuss them. But hopefully this is making sense. I will post some solutions to some of the practice problems, but everything, you know, is a variation of what I did it with different numbers. Like the techniques are literally always the same 1, 5, like, there's no, it's just like different numbers. But if you understand well an example from each type, then it's all the same, but with different numbers, and that's it. So let's stop here, and because we're almost run out of time, and I wouldn't have time to do another one. Okay.